We have this new simulation. It's to do with K-Theory. K-Theory, everyone loves a good piece of maths, but this one actually doesn't have any equations on it. That's great, isn't it? No equations is awesome. We have a demo mode running. I mean, you can interact with it yourself. And the demo should start 10 seconds after the user is not interacting with the page. So it's already up and running. It should run in a loop. We gave the code to Gemini 2.5 Pro, and we listen to 5 minutes of overview. And we'll go from there.
You must see this. It's a simulation of K-Theory.
K-Theory? Sounds like a conspiracy theory involving breakfast cereals. You won't believe what they're really putting in your Cheerios. It's the letter K.
Not quite. It's a mathematical tool to classify complex systems. Think of it as a way to find the hidden patterns in the chaos of life. The website calls it an interactive analogy.
The chaos of life? You mean like when you're trying to fold a fitted sheet and you suddenly question all your life choices?
Exactly. Or on a grander scale, think about things like ecological systems or even the stock market. It's all a beautiful mess. K-Theory is about understanding the topological charge of that mess.
Topological charge? Is that what I get when I plug my toaster in with wet hands?
Close. Think of it like this. You have a field of arrows all pointing in different directions. A vortex is a swirl, a point where the arrows spin around. K-Theory counts the net number of these swirls. A vortex is +1, an anti-vortex is -1.
So if my life is spinning out of control in a counterclockwise direction, that's a +1? And if it's spinning clockwise, it's a -1?
You've got it. And here's the cool part. If you have a vortex and an anti-vortex, they cancel each other out. Your K-class, the total score, becomes 0. The system looks complicated, but its net charge is trivial.
Ah, the principle of canceling out my bad decisions with equally bad but opposite decisions. I'm familiar with this. Like eating a whole pizza, but then having a diet soda. The K-class of my stomach is 0.
That's a creative application. But you've grasped the core idea of K-Theory. Vortex plus anti-vortex equals trivial. The interactive simulation on the website lets you add these vortices and anti-vortices to see how the K-class changes.
So K-theory is the mathematics of it all evens out in the end. Sounds suspiciously optimistic for a data scientist.
It's not about optimism, it's about structure. The K-class is a topological invariant. That means it's robust. You can't change it with small nudges. You can comb the field all you want, but the only way to change the K-class is to add or remove a whole vortex.
So no amount of rearranging the deck chairs on the Titanic will change the fact that you've hit an iceberg. You need another iceberg to cancel it out. Got it.
Or, more practically, think about data. The website mentions using this for biomedical data analysis. Imagine you have a ton of data from a tumor. You could use these ideas to find the significant, robust structures in that data, the vortices that tell you something important is happening.
So K-theory helps you find the tumultuous swirls in a sea of boring data points. I like that. Does it have any other fun applications?
Well, it has applications in string theory.
String theory. The theory that says the universe is made of tiny vibrating strings. So K-theory is how we know if the universe's strings are tangled up in a cosmic knot.
In a way, yes. It helps classify the complex spaces that string theory predicts. The website even talks about extending the analogy to higher dimensions and using it to visualize things we can't see.
Higher dimensions. So you're saying there's a dimension where I can eat all the pizza I want, and the K-class of my health is always +1. Sign me up.
I'm not sure that's one of the dimensions K-theory has discovered, but it does show us that even in the most chaotic-looking systems, there are fundamental, unchanging properties.
So K-theory is like a comedian's punchline. You have all this complicated setup, all these details that seem random, but then there's one simple, elegant twist that makes it all make sense.
I've never thought of it that way, but that's a perfect analogy. It's the punchline of the universe.
And the universe, my friend, is a very, very weird joke. I'm glad we have mathematicians like you to figure out why it's funny. Now, about that breakfast cereal conspiracy.
Yeah, that was pretty good. That was Gemini. You can check the tool yourself. You can interact with it as well, or run pre-simulated stuff. Because apparently K-Theory is very hard to visualize while we're giving it a crack. Everything we do, by the way, is available on Biomedical.com. Go check out the website. Let us know what you think. Let me know if you have any questions about any of the tools or any suggestions as to how we could improve them. Will be more than welcome as well. Do let me know if you use a K-Theory, or if you're a mathematician, if you can actually check that the code is correct for this. It doesn't look like the magnet simulation we have. Yeah, this one here, I haven't looked at it for a while. Can add up to 4 magnets in this one. Can move them around, rotate them, and see the magnetic fields. Hey, can you give one sentence on each web application?
Absolutely. One, K-Theory, an interactive demo that visualizes topological K-Theory using vortices and vector fields, illustrating topological invariance. 2, an interactive magnet simulation that lets you add, move, and rotate magnets, visualizing magnetic fields and forces in real time.
Okay, and how they related to one another?
They go serve as educational tools that visualize complex abstract concepts in a tangible way. The K-Theory demo illustrates topological invariance, while the magnet simulation visualizes physical fields and forces. Both rely on intuitive, interactive visualizations to help users grasp abstract mathematical or physical principles.
But how are magnetic fields actually relevant to the dynamic analogy in the K-Theory web application?
In a direct sense, the magnetic field in the magnet simulation and the topological concepts in the K-Theory demo are quite different in their physical and mathematical bases. However, both applications illustrate the idea of invariance and stability under certain transformations. In the K-Theory demo, the K-class remains unchanged unless you add or remove a vortex, similar to how certain topological features remain stable despite local changes. The magnet simulation shows how the overall magnetic field remains consistent unless you change the sources. So both highlight the concept that certain global properties are invariant under local changes, which is a nice conceptual link. Absolutely. Think of it this way. The K-Theory demo shows how some topological features are like secret invariants that don't change no matter how much you twist or turn the field, kind of like how a magnet's overall magnetic field stays consistent no matter how you move it around. So both demos are all about how certain global properties hold steady, even if you fiddle with the details. If that sounds cool to you, definitely check out both tools and let me know what you think. Of course, you can check out the K-Theory demo at bionichaos.com. K-Theory. And the magnet simulation at bionichaos.com. Magnets. Go explore them and feel free to share your thoughts. Great question. The magnet simulation can actually be pretty relevant to biomedical data science because the principles of magnetic fields are at the heart of technologies like MRI, which is a cornerstone in medical imaging, understanding how magnetic fields interact, how they combine, and how they produce forces is super useful for visualizing and interpreting biomedical data. So the simulation gives a hands-on way to understand these concepts, which can definitely help when dealing with complex medical imaging data. It's a neat connection. The K-theory demo is a bit more abstract, but it's still relevant in a biomedical context, especially in areas like computational biology and the study of complex biological systems. The idea of topological invariance can be applied to understanding the stability of certain biological structures or networks, kind of like how certain properties of proteins or cellular structures remain unchanged despite various transformations. So in a sense, it helps in understanding the underlying stability of complex systems, which is super handy in biomedical data science. It's a cool out-of-the-box connection.
Yeah, okay, that was ChatGPT assuming 5, version 5 or another one. Well, that's the voice model, so it will be different model altogether, potentially. Everything we do is available on bionicchaos.com. Go check out the website. Let us know what you think.